As mentioned, when we were devising a strategy for deriving backpropagation, our first step involved finding generic expressions for weight derivatives starting at output layer L. So if you consider some weight between a neuron, let's say the youth neuron of layer L-1 and the VF neuron of layer L, and then we denote the weight as W, U, V, L. We can then look to find an expression for the partial derivative of C with respect to the weight going from neuron U to neuron V in layer L. And that would be our first generic weight derivative. So the question is, what's this? Recall that when we were outlining which input factors affect the cost function, we saw that the cost function was a function of the activations at the output layer. So the activation at neuron 1 at the output layer L, and the activation of neuron 2 at output layer L, that is these activations right here, all the way up to the nth neuron. And when we examined the individual neurons, we saw that the neural output, that is the activation of the neuron, for instance, if we consider the VF neuron of layer L, it was given by AVL, the activation at neuron V, is equal to some function, the activation function, applied to the weighted input at neuron V. And a weighted input was given as the following linear combination, where you take the activations from the previous layer, that is layer L-1, you scale them, and then you add a bias term to the VF neuron. So this would be the weight from an arbitrary neuron in the starting from the L-1 layer, going to neuron V at layer L, multiplied by the activation at the neuron from the previous layer. Then you just add an individual bias term. So we see here that the activations are functions of weighted inputs, which mean we can break this down further like this, where the activation at neuron 1 is a function of the weighted input at neuron 1. And the activation at neuron 2 is a function of the weighted input at neuron 2, and so on. Now to complete this diagram, we need to include that each weighted input is a function of our differentiating variable WUVL. And this is the case because according to chain rule, when we take a deeply composite function and we unpack it, at the end, the innermost variable needs to be differentiated by the variable we're intending to differentiate the original function with. So here, every weighted input will potentially be a function of our differentiating variable. Now, when applying the chain rule with the aid of this diagram, what we're going to do is we're going to start at the root, and then we're going to traverse our way to each leaf node of this tree diagram. And along the way, we're going to note the derivatives going from one level to another. And then we're going to multiply each derivative term as we traverse down the branch. And once we've done that for every branch, we're going to sum all these derivative terms across the leaf nodes. So just to show how this is done, we start from C. As we go from C to activation 1, we'll consider the partial derivative of C with respect to activation 1. As we go from activation 1 to the weighted input at neuron 1, we'll consider the derivative of activation 1 with respect to the weighted input at 1. And this is a regular derivative, not a partial derivative, because activation, as you can see here, is just a single variable function of the weighted input. Now, the weighted input, as you recall, was a linear combination of several weights and biases. So the weighted input itself is a multivariable function, and therefore when we consider the derivative of the weighted input with respect to w uv, this is going to be a partial derivative. And then we're going to do this for every other branch. So starting here, we would get the partial derivative of c with respect to a and l. Here would get the derivative of the activation at neuron n with respect to the weighted input at neuron n. And here we'd get the partial derivative of c, because once again, the weighted inputs are multivariable functions. Now what we're going to do is we're going to traverse each branch, and we're going to multiply the terms, and then we're going to add them across each branch. So this means that the partial derivative of c becomes this term multiplied by this term multiplied by this term, which is partial derivative of c with respect to activation at neuron 1 multiplied by the derivative of the activation at neuron 1 with respect to the weighted input at neuron 1 multiplied by the partial derivative of the weighted input with respect to the weight we're trying to differentiate the cost function by. And then we're going to do this for every branch in this T diagram. So it's going to be all the way up to partial derivative of c with respect to the activation at neuron n multiplied by the derivative of neuron n with respect to the weighted input at neuron n multiplied by the partial derivative of the weighted input at neuron n with respect to our weight. Now to write this more compactly, we can just write a summation where you have some sum from I to n of the partial derivative of c with respect to an arbitrary activation at neuron I at the output layer L multiplied by the derivative of this activation with respect to the weighted input at that neuron multiplied by the partial derivative of the weighted input with respect to our weight. Now to continue, we need to compute this derivative right here. So we're going to continue along here and consider the partial derivative of the weighted input at some arbitrary neuron I with respect to our weight w uvl. Now this is essentially asking, if I take some arbitrary neuron I at the output layer and I change this weight, how is it going to affect I? Well, we can see here that the weight is only incident to the VIF neuron. So this weight can only affect the VIF neuron. If I 100x this weight, this w uvl, I multiply by 100, it's not going to affect the activation at the nth neuron, because this weight is not even touching the nth neuron. So it only affects the VIF neuron, which means that the weighted input, the derivative of the weighted input with respect to this weight at any other neuron than V will become 0. So let's write this down. When I is equal to V, we get the partial derivative of the weighted input at V with respect to our weight. Now this was a non-zero term because the weight here actually affects the VIF neuron. So this is when I is equal to V. And when I is not equal to V, we get 0. So now let's try to compute this partial derivative right here. We have the partial derivative of the weighted input at neuron V with respect to our weight. If you recall, when we examined the individual neurons, we saw that the weighted input at a given neuron V was equal to the sum of weights. And since we already used I in a previous summation, let's just use J here. So J goes from 1 to n. of the weight from J to V multiplied by the activation of the Jth node in the previous layer, plus some bias term at the Vth neuron. Now distributing the derivative, we get that this is equal to the sum of from J to N of the partial derivative of our weight UV for this term, which is V JV plus the partial derivative of our weight UVL with respect to the bias term. This term just cancels to zero because our bias term at neuron V is not affected by the weight. They're two completely separate network parameters, and we change them independently. Similarly, if we consider the weight, an arbitrary weight to the output layer and an activation from the previous layer, we see that this weight, WUV, does not affect an activation from the previous layer. It doesn't affect the activation at the youth neuron either, because the activation has already been calibrated by the weights and biases from the layers before the L-1 layer. So even if you 100x this, it's not going to affect an activation from the previous layer. If there's a massive tsunami in front of you and it's moving away from you, it's not going to hit you. So that's sort of the idea here. Similarly, this weight is not going to affect any other weight from the previous layer to the output layer, because the weights are network parameters and they're set independently, or we could set them independently. If I pick 100 for this weight, it doesn't force me to pick any other value for the other. So changing this weight doesn't affect any other weight. In this case, this would be the weight from neuron 1 to neuron 1 at output layer L, excuse me. Changing this weight is not going to affect any previous layer activations, and it's not going to affect any other weights, but it's going to affect this weight. Changing this weight is going to affect itself. So we can go back to our expression and see that we get the sum from J equals to 1 to N of our activation, which we can take outside of the differentiation because WUVL doesn't affect the activation. And we get this term right here. And this term, if we decompose it further, we see that the derivative of the weight from some arbitrary neuron J at layer L-1 to neuron V at layer L. If we talk about any other weight than UVL, than the weight from neuron U to neuron V, we get 0 when J is not equal to U, and we get the partial derivative of weight UVL with respect to weight UVL, which is just 1 when J is equal to U. So if we go back to our sum, we see that this term becomes 0 when J is equal to any other value than U, and it becomes 1 when J is equal to U. So we only get a non-zero term when J is equal to U, which means that we get A U L-1, which is the activation of the youth neuron at layer L-1. So the partial derivative of the weighted input at neuron V with respect to the weight from U to V is equal to the activation of the youth neuron at layer L-1.